Okay, I think we're good to go. Before we get started, just a little bit, some ground rules here. I'm going to be asking you guys questions. I hope you guys ask me questions. This will be good. All right. So, who here is using Redshift? Okay. All right. Who here knew about Redshift before this conference? All right, that's good. That's good. We would have been in trouble if nobody knew about it. I just thought this was funny. It has really nothing to do with the presentation. But if you're a data scientist, you should probably know in advance if you're going to get hired somewhere. I just thought that was interesting. Okay. Who am I? My name is Eric Snyder. I work for Chariot Solutions. I've worked for Chariot non-contiguously for about 5.5 years. So I have a fragmented employment history, but that's where I am right now. I did not put up my Twitter handle. I don't know if that's going against convention, but you'd find it incredibly boring, not particularly technical, a lot about soccer. If you're into soccer, it's at SNYDEREP. So otherwise, don't worry about it. Right, so when I came up with the name for this presentation is Amazon Redshift, the game changer. Clearly, I did very little research ahead of time because it's been taken by quite a few people. There's about 18,000 hits on that, so too late to change that. But right, so game changer, I'm sure we all know what the definition is, but we'll just go over it again. Something that affects a significant shift in the current manner of doing or thinking about something. So Redshift is a new data warehousing solution, right? There's lots of them. That's clearly not a game changer. It's relational. Well, there's lots of those too, right? It's a relational data warehousing solution in the cloud. Is that new? Not really. So what makes this a game changer? I'm not making any conclusions. I want you to decide. Right? So this is Amazon's definition of Redshift. And the reason I put this up here is it's a good place to start. We can break down what they say it is, and then we can decide if we believe them. So they say it's a fully managed petabyte scale data warehouse service in the cloud. If you didn't know, it's based on Paracel. I'm not quite sure the right way to pronounce it. I don't know what the arrangement is, if it's just licensed, if they forked it and contribute back to Paracel. I'm not quite sure, but that's where it comes from. Fully managed, right? So who here is in AWS land today, right? Or has dabbled? I'm sure everybody's dabbled a little bit, right? So that's the promise. That's the genius of AWS. They take care of everything. They're your cloud babysitter for you, right? So AWS takes care of provisioning and configuring all of your instances from, we'll get into what nodes are in terms of Redshift, but it's suffice to say, the more data you have, the more nodes you need. And Amazon will provision those for you, will configure those for you, will spin them up. They'll monitor your cluster. So if you have an instance that goes down, they'll do some, it's not clear what they monitor exactly, but we've seen instances that degrade, get replaced automatically. You don't even have to worry about it. They patch Redshift. There's a weekly patch window that you have to define, the maximum of which I believe is half an hour. But typically they'll patch in about 5 to 10 minutes. And during that time, your cluster is unavailable, but it's a nice thing for them to do, right? You don't have to worry about it. Security patches, critical patches, minor feature updates, that kind of thing. You can prevent them from doing major upgrades and rebooting your cluster, but the patching is nice. Backups, it's, really, you don't have to think about it. It's continuous backups, incremental backups, and they happen constantly. You just have to specify how long you want to retain them for. Clearly, there's a cost associated to keeping these snapshots around, and you can decide what that cost will be. And then monitoring. If you're in AWS land and you're familiar with CloudWatch, all of the dashboards, the consoles, the various metrics you can create, the alerts you can specify when you go in and out of bounds of whatever limits you decide, that's all baked into Redshift as well. So to sort of go over it again, there's no devices to purchase. That's the important thing. Clusters, when you want them, you click on a button or you make an API call and you'll have a fully functional data warehouse in, say, 10 minutes, right? It obviously depends on how big you want it to be, but I think that's pretty impressive. And you'll get an endpoint that'll come up right away. So within 5-10 minutes, you'll have your JDBC URL, your ODBC URL, whatever endpoint you use to talk to the warehouse. It'll be there. We talked about snapshots. They're automatic, continuous, and incremental, or on demand. I didn't mention that. So if at any time you want to take an on-demand snapshot, click of a button, single API call. Petabyte scale. Okay, this is another claim by Amazon. What does that mean exactly? So there are different types of nodes in a cluster. We'll see a diagram of what a cluster will look like. But basically, there's 2 node types. XL, 2 terabytes per node, and 8XL, 16 terabytes per node. So if you do the math, that's anywhere from 4 terabytes up to 1.5 petabytes, hence petabyte scale. Cluster node types must be homogeneous, so however you configure your cluster, they all have to be the same node type. So you have to make some decisions up front. But the important bit is that you can change on the fly whenever you want. So that's very cool, right? So holiday season's coming up. You have clickstream data that increases with retail traffic, for example. You might need a couple extra nodes in the next month or 2. Really quickly. So that's easy to do. A single API call, couple clicks of a button on the console. So this might be the most important slide in the presentation, at least for some people in this room. This is a game changer. If you look at all the other data warehousing products that are out there, these are the costs. There's different node types. We talked about XL versus 8XL. You can get on demand. You can get 1 year reserved, and you can get 3-year reserved. Clearly, obviously, if you purchase capacity in advance, it's cheaper for a lot of reasons. And Amazon, obviously, they want to know their demands in advance. They give you a significant discount. I'm pretty convinced that they backed into that $1,000 per terabyte per year number from the 3-year reserve, because it's a nice round number to say. It's good press, and I've seen it before. But it's pretty cheap. Now, this doesn't answer the question, do I need a fancy, cloud-based relational data store, or can I get away with something else? This doesn't answer that question, right? So, if you have, 1 terabyte of data, can you just, come up with some partitioned scheme in Postgres and use that? Of course you could, right? So that would clearly be less than $1,000 per year per terabyte. But for this kind of solution, that's a game changer. Now, everybody's eyes should be rolling at this point when they look at the slide in this room, and some people should be angry because there's clearly not enough information on this slide, right, to come to any definite conclusions. The whole point of this slide is to sort of provoke people into investigating further. This is one particular observation, and to get the details, please go to that link, right? So in one particular case, this poster set up a set of queries that they ran against Hadoop. Click on the link and it'll tell you what version of Hadoop, what version of Hive they're using, HDFS, HBase, all the details. They ran the same query every 30 minutes over a period of time, and it was a factor of 10x reduction in cost, Redshift over Hadoop. 10x seems to be a pretty popular number thrown out there for various cost differentials between Hadoop, Hive, and Redshift. Again, please, your mileage may vary. Your version of Hive may vary, your version of everything may vary, but 10x is thrown out a lot. And that's definitely a game changer. Redshift in the AWS universe. So this is sort of a primer for people that aren't necessarily doing much in Amazon Web Services area. But a cluster right there, essentially the 3 horizontal buckets are your compute nodes. So those are your XL nodes or your 8XL nodes. And the horizontal one is called the leader node. The leader node itself carries no expense, but it's essentially the coordinator, and it's the point of contact from all clients. So all clients connect to the leader node, and we'll talk about the compute nodes in a few slides. But so to query and perform whatever. You have clients. To get data into S3, there's multiple ways. Sorry, to get data into Redshift, there's multiple ways. But typically, it's done via S3. And if you're not familiar with S3, it's just storage. It's storage. You can read, write, and delete objects in the cloud that are anywhere from 1 byte to 5 terabytes. And you can get at S3 via SOAP, a SOAP API, or RESTful calls, and whatever your language of choice is. There's tons of libraries out there to do that. So, and then you can export data out to S3. There's also the ability to import data via DynamoDB. And if you're not, anybody familiar with Dynamo at this point? Okay. It's a fully managed NoSQL database service. It's SSD based. It's got some unique features to it. We're not really going to get into it, but it's another way to get data into the warehouse. Right, so to get data into Redshift, it's simple. I'm not really going to get into the specifics of this too much, but you can give it your destination table. Where in S3 is my data coming from? Your credentials are your AWS key and secret key, which are tied to web service, or your AWS users, which have security policies, and there's a whole chain of things that go along with that. And a similar thing you can do from Dynamo. It's important to note that you can also do a traditional SQL insert, but Redshift, like a lot of data warehousing solutions, is optimized for reads, not for writes. So inserts are slow. So bulk insert via standard SQL insert is generally not a good idea. And one of the reasons for that is that, well, there's many reasons. One of which is a column store. We'll get into that, which is optimized for reads. But transactions in Redshift always run in a serializable isolation mode. So you tend to have conflicts and serialized transactions in Redshift when doing inserts. So copy is your best option. Copy is atomic, as you might expect. Oh, and if you're curious about that read ratio parameter, basically you're specifying the percentage of DynamoDB's provisioned throughput for the load. So basically we're saying use 50% of our provisioned read throughput for this table to load the data. So if that was 100%, that would indicate that we're going to use all of our I/O for loading data from this table into Redshift, and nobody else can read that table. So, and copy can load data in parallel. It's actually quite impressive how much data you can load, and it'll do a lot of loads in parallel. So this is a game changer that I don't know if anybody caught. I don't know if it means anything to anybody here, but it meant a lot to me. Did anybody recognize something really significant here? Anybody? Doesn't stand out to anybody? All right, I'll give you a clue. Copy, right? So what? Copy. No? Nobody recognized it yet? So what? Postgres. PostgreSQL. Syntax is very familiar, right? Why is that a game changer? Well, if you think about it, if you can have a data warehousing solution, a cloud-based data warehousing solution that is compatible with Postgres, that means a lot. Oh, Postgres-ish, I should say, right? So how is it similar to Postgres? Well, it's the same over-the-wire protocol. That is the biggest game changer that I can possibly think of for this, aside from the cost. That means all of your BI tools, all of your existing solutions, all of your existing custom code that worked with Postgres should work with Redshift. Now, there's some caveats to this, which I'll get into, one of which is it's based on an older version of Postgres, Postgres 8. So some Postgres 9 drivers may or may not work. Your mileage may vary. What else is different? A lot of Postgres-specific extensions are not supported, but there's extensive documentation for that. So that is why this is a list of partners, official partners, and other companies that have already integrated their solutions with Redshift, and why there's so many so quickly. Redshift is still fairly new. Came out of public beta, what, 6 months ago, maybe 8 months ago. And there's a lot of integration already because it's Postgres compatible. So this is what's not supported. Table partitioning. We'll find out why that's pretty significant, but if anybody's used Postgres table partitions in the past, it's a pretty powerful feature. Essentially, it's similar to a lot of other relational data store partitioning schemes. You can create subtables for subsets of information, like, I don't know, one table per month of URL clickstream data, right? And then when you query that table, basically the query planner is smart enough to know what partition to go after the data. It makes intelligent decisions. That is not supported in Redshift, so that's important to know. Significantly, constraints are not supported, at least these constraints in Redshift. Unique constraints, and why is that? Anybody care to guess why you can't support unique constraints easily in a distributed relational data store? No? It's distributed, right? I just gave it away. Right, so I suppose it could be done, but I imagine it'd be a very difficult thing to do and not particularly performant. Primary keys and farm keys, they're supported in the sense that the syntax is supported, and supposedly the query planner takes them into account. I don't know if I've ever seen evidence of that. Maybe it does, maybe it doesn't. And check constraints are also not supported, unless you count null constraints as check constraints. They are supported. Indexes are not supported. Well, that throws some people through a loop, right? So we'll see why that doesn't matter particularly in a bit. Use-defined functions and stored procedures, that would be fantastic, but they're not supported, not yet anyway. It's a caveat on all this, is not yet, who knows. And full-text search is not supported. Old school ACID goodness, right? So why would I have a slide about there's nothing new here, right? Well, it's kind of not new because it is new, right? There's so much momentum behind NoSQL data warehousing solutions. This kind of is professionally new. It's a game changer in that we're yet again talking about a relational data store. It's not base, which is NoSQL, basically available, soft state, eventual consistency, right? So just relational 101, we have atomicity, transactions guarantee all or nothing mutation of data. So we have real transactions with Redshift. Consistency, kind of a small c in this case, but basically we ensure that transactions bring the database from one valid state to another. Sure.
If you don't have any key constraints, then what does a transaction guarantee?
Sorry?
Well, because like normally a transaction, you have a foreign key or a primary key, you're saying you don't want duplicates, and that a certain check fails, then the whole transaction is rolled back.
Right, so it's not going to guarantee that you won't create duplicates. That's not a guarantee that you can get, that's true. Yeah. So any solutions that you want to put in place to guarantee that doesn't happen are going to be external to Redshift. They're going to be at some other level. So if you could fail other constraints like not null constraints or type constraints, string lengths or whatever. So there's other reasons for and obviously you can always transactions can fail for other reasons. So, but that's a good question. Oh, I'm sorry, I didn't repeat the question like I was supposed to. The question was if you don't have primary key constraints, then sorry.
Well, you were just saying that you don't want to do like per line inserts, and it seems like you're putting everything in batch. So like it's great that you can say it's transactional, but if you don't have any of these things, there's not a huge win. What would you do?
Oh, what's the big win then? And it's transactional. Well, I mean the fact that batch inserts themselves are transactional, so that's good. So if you're executing one copy over a set of data in an S3 bucket, you still can have invalid data that's in there, right? And that can fail not null constraints, type constraints, so that copy itself is atomic. So you might have 20 billion rows loaded in one copy statement, and that in itself is one transaction. So that's pretty useful too. Isolation you still have, right? So that's no different. So the effects of an incomplete transaction aren't visible outside of that transaction. And durability, so a completed transaction will remain completed, right? Even through power outages and hardware failures and other failures. You can unload data, dump to S3. The syntax is pretty hokey, to be honest with you. The fact that the queries have to be quoted in such a way, requiring some unique gyrations to escape things sometimes, but it works. And the interesting thing about this is it unloads data in parallel by slice, and we'll talk about slices. But basically, one query will produce X number of flat files, or flat objects, I guess they're not really files, in S3. And that can be very useful. Right? So Redshift is a parallel machine, so each node that we talked about, the XL or 8XL nodes, they all have their own OS, their own memory, and directly attached storage. It's spinny disk. It's not flash. It's not SSD, not yet anyway. And the leader node, like I explained before, is the coordinator. So the leader node, it manages the distribution of data and query processing tasks. So that's where the planner runs. It actually, we'll get into this in a little bit, but it actually generates C++ on the fly, compiles it, and distributes it to the compute nodes. That's pretty interesting. So every compute node has a number of slices, and the number of slices equate to the number of compute cores on the node. So if these were XL nodes, each XL node would have 2 slices, and if they're 8XL node, each would have 16 slices. So that is your level of parallelism, right? So if you do it right, then you'll have every node in your cluster will be processing the same step of the query at the same time, and they'll all finish at the same time, and the data will all come together, and everybody's happy. If you do it right, it doesn't always happen. So the goal then is to select a key, a distribution key, which we haven't talked about yet, that evenly distributes data across the cluster. This is not that different than other data warehousing solutions, but it's still very, very key. And as a side note, if you don't supply a sort key, then the tables are just evenly distributed across all the slices. So this is just an example. Distribution key is hashed, and the leader node distributes the data to all the slices based on the hash. Right? So user ID could be a good example. That really comes into play when you have joins involved. So when all the data participating in a join is located on the same node, then the query engine doesn't have to do any distribution. Right? So this choice of distribution key is very, very important. And it depends a lot on the types of queries you're doing. Right? Do you have a multi-tenant scenario maybe where you have the leading part of what you query on is maybe a client ID or something like that? Maybe that's your distribution key, or maybe a better thing would be like a user ID. You really have to decide, and it depends on your usage patterns. And sometimes it makes sense to come up with different materializations of the same table with different distribution keys to satisfy your query patterns, right? So you might have a table foo with the disk user ID. You might have like foo prime, which has the same facts with a different distribution key.
Is there any way to plug in your cache?
No, not yet. Yes, exactly. Okay, so that key choice is very critical. If you distribute data unevenly, then obviously you'll have some slices doing more work than others, right? So maybe user ID is not such a good key if you're querying across user ID, right? Or no, if you're querying on user ID, right? Because then you have one slice that's got all the data for a specific user ID. It's going to do all the work. So in that case, it's not a good distribution key. The engine, basically at the bottom is a step, and a step is just an individual operation in the plan. So it's what you would think of, a scan of some materialized data, an aggregation, a sort, just what you would expect to see in an explain plan. That's the bottom part of it. That's what happens individually on slices. Above that, they have a logical concept called a segment, which is just some number of steps that can be executed by a single process. Segments are what get distributed. So when it generates the C++ code, it generates C++ code for segments and then spits it out to the slices where they're run. Each segment has to begin with a scan of data, and it ends with either a materialization step, which leads into another segment, like some temporary store of data somewhere, or networking activity. Basically, here, spit your results back to the client. And above that, they have what they call streams, which are collections of these segments that have to be executed consecutively. So they have, I don't have an example here, but there's a lot of system tables that you can query where you can see all this activity. You can see what slices are processing what steps. You can get an estimate in your head of when these queries are going to finish. So it's pretty, there's a lot of visibility into what's going on. So I sort of mentioned this before, but these are the different possibilities when you do a join. When co-located joins are possible, if you run an explain plan, which, by the way, if you've looked at PostgreSQL explain plans, they're excellent, and they're even better on Redshift. So not only do you get the normal information, but you get all the information you need on the distribution of data. So you can see exactly what's going on. So if you see ds none on a join, it means no data is being distributed, right? Co-located joins are possible. That's the most optimal situation. Sometimes a broadcast copy of an inner table to all the compute nodes is necessary. That sometimes is necessary when there's a smaller table, maybe a lookup table, for example. That'll happen. You can have inner table or both tables distributed as well. So when you look at your explain plans, you can look at this and then get some ideas as to changes you might have to make or changes in distribution key or what's going on. That's just a few examples. As I mentioned before, it's a column store. Again, that's not a game changer. Column stores have been around for a long time. But it makes sense in this situation why it's so useful. So on the left is a typical relational data store where data is stored contiguously, attribute by attribute. Rows are stored contiguously. That's useful in like an OLTP scenario. But in a column store, data is stored together by column. Typically, it's a file each. We're not privy to the internals of Redshift, so you can't quite tell exactly how that happens. But for example, user ID, event time, and SKU, they may all be a row in a table, but they're stored in separate, possibly files. So all the user IDs are stored contiguously, event times, SKUs, or whatever facts you may have. And that's very efficient for read-only queries for a bunch of reasons, right? So if you're smart about how you query and you don't just select star everything, there's a lot that can be skipped, right? So you only have to read files that are accessed that are specified in your query. There's no need to store duplicate values. Redshift provides with compression. They call it encoding, which is really a terrible name for it. It's not encoding, it's compression. So for different types of data, you can say, I want to use LZO compression. I want to use run length compression. I want to use delta compression, which if you have dealing with integer values, maybe you only want to store the difference between this row and the row before it. And that way you'll save a lot of space. They also have a command that you can run against your tables. It'll analyze a sample of your tables, and it'll tell you what compression you should be using. This saves a tremendous amount of space. I can think of specific examples where we saved like 30% of the space in a particular cluster. It's easier to cache data in a column store. It's excellent for aggregation. So if you can imagine, if it's not SKU, if it's some aggregatable value like a price or something like that, it's easy to query over a series of contiguous prices. There's a penalty for decompression. Based on some earlier experiments I did, it's roughly 10%. So you don't have to compress your column data, but you can. Zone maps and sort keys. So I mentioned before that there are no indexes, right? So, how can it possibly be efficient if there are no indexes? There is an index in the sense that it's a traditional clustered index in that the data is stored in a sort order, but it's only one order, right? So that's key when you're coming up with your schema layout. So the boxes at the bottom, imagine those are blocks on disk, right? They're pages on disk. And Redshift uses large block sizes, 1 megabyte. So they read 1 meg at a time, right? For each 1 meg, there's a zone map, which is sometimes incorrectly called a skip list, I've seen. But it tracks the minimum and the maximum value of the column for each block. So you save a lot of I/O that way. It can just scan through these large block sizes, instantly detect whether it needs to continue scanning those blocks or it just skips. That's clearly going to reduce I/O dramatically, but it's only efficient when the data is sorted, right? And that is the fun part, getting the data sorted. So in this case, you can see there's a range query between a specific set of dates. It skips the first block and then reads the next two and skips the last one. Any questions? No? This is all old stuff? That makes sense? Okay. The dreaded unsorted region. Okay. I have to say, I hate the unsorted region. The unsorted region is a pain, okay? But if you have a new table and you load the data in via a copy statement or an insert, it will, the very first time you do that, it will sort the data based on whatever sort key you provide, right? So it takes care of that for you. Everything's sorted. Zone maps work efficiently, and your queries run great, and everything's happy, right? Then your second day of using the warehouse happens, and you have a non-empty table, and you load the second day's worth of data in there. That second day's worth of data goes into what's called the unsorted region. And in that case, every time you query that table, it's quite likely that an on-demand sort is going to be needed against that unsorted region, right? And that's clearly going to sap some efficiency out of your queries. A great deal, actually. So vacuum. I get headaches every time I talk about this. Vacuum is not the same as vacuum in Postgres. How many Postgres people are there here, by the way? A bunch? 2? No? Okay. It's not the same as Postgres, only in the sense that you need vacuum to reclaim space after you delete data. So in Redshift, when you delete data, it's just a tombstone. It doesn't actually reclaim space at that time, and vacuum takes care of that. But what it does is it resorts rows based on the sort key that you provide. So essentially, when it's finished, it eliminates the unsorted region. The key there is what I said, when it's finished, right? Because sometimes it won't finish. The bane of my existence for weeks. So if you haven't gotten the gist, I don't like vacuum. So it's not an option in many scenarios because we'll talk about the multi-tenant scenario, but there's many scenarios where it just doesn't get the job done. It'll just run and run and run and not complete. It does sap a great deal of resources from your cluster. I don't have a percentage that I can give you, but I know that it's significant. And Amazon's recommended alternative is they call it deep copy. So it's kind of funny, they came up with this term deep copy, and all that means is create a new table, select the data from the old table, insert it into the new table, and then it's sorted. So you're all good to go, right? Except for the fact that, well, while you're doing that, you can't actually insert into the original table. And then you also need the space available to insert that original data into the other table, which is a problem because the reason it doesn't finish vacuuming in the first place is because the original table is probably too large. So the multi-tenant scenario, this is pretty common, right? We all have businesses or clients that have clients. So typically, in a lot of cases, you're going to get at your data by some kind of client ID or account ID or something like that. So it's typical for that to be the leading part of your sort key, right? That sort of makes sense, right? You think, well, if all my queries are going to always specify a client ID, if it's the leading part of my sort key, then Redshift will be smart. And it's just going to skip all the other blocks that have client data from other clients, and it's just going to read the data from the clients that I care about. That's true, and it does work like that, and that's fine. Except, let's say we have our day after day loading scenario again, right? So you load a table, all the data is sorted by client ID and time, you're good to go. Next day comes in, client 1 gets some facts, client 99 gets some facts, right? Well, they're in the unsorted region. I got to get that data back where it belongs. So I run vacuum. So what vacuum has to do is it has to insert data at the very beginning of the table for client 1 and at the very end for client 99. I don't know why, but for whatever reason, this implementation is highly inefficient in this particular scenario. You can actually do an experiment and do an insert at the beginning of a table, a large table, right? And then do the same thing at the end and run vacuum after each time. If you insert it at the beginning, its vacuum will run exponentially longer than it will if you insert data at the end. So that is a problem that is not yet completely solved. In order to solve that problem, what you could do is switch your keys so that time is first and your client ID is second. And that will work, except there's inefficiencies in the queries then, right? So you may skip some blocks of data because you're filtering on time, but then you're not skipping the data that you could by filtering on client. It does work, but it's not particularly efficient. This is one reason why true partitioning would be helpful, right? So if you had one table per client, you could do that, right? You could even do that in Redshift right now, and then create a view across all these tables. The only problem is there's a limit of 1,000 tables in a Redshift cluster, right? So if you've got 5 clients, you can get away with it. The other problem is it's not smart. So if you create a view over one table per client, then the query planner doesn't push filters down. It's not smart enough to know not to query all of those client tables, right? And then bring the data up and then sort out the ones that you need for a specific client. So that, I think, is a big gap that I hope they're addressing in the near future. It's definitely a little painful. We kind of talked about this, but relaunch from snapshot, node replacement, this is actually very, very cool. In either scenario where you have a node that goes away, and let's face it, this is the cloud, things happen, right? You guys are familiar with Netflix and Chaos Monkey? No? So Netflix has a product called Chaos Monkey, which will go out to their Amazon EC2 instances in production and just terminate them. Sounds crazy, but it keeps their architecture very robust, and it keeps their ops team on their toes. Well, Amazon is kind of their own Chaos Monkey, right? These things happen all the time. Your nodes they disappear. You have to plan on it, right? For whatever reason. Sometimes your instances get retired, and you forget that they get retired, and then they disappear, right? So this can happen in Redshift too. I've seen it happen once, where a node basically died, right? So when that happens, what Amazon does is it'll spin up a new node for you, but in the meantime, well, what do? I need to query data, right? I can't just forget about data on that node, right? Because it's directly attached storage. If your node goes, well, there goes your storage, right? So now I have a new node without my data on it. Redshift is really smart. It'll stream data. First, it'll stream data onto that new node based upon the most frequently accessed bits of data. So it'll try and get that data onto the new node first. And then it'll also stream data directly from S3 into the query engine. It's slow, slower, maybe an order of magnitude slower, but the data is always available. So that's pretty cool. And the same thing goes for relaunch from a snapshot. So if you take a snapshot, a manual snapshot or an automatic snapshot, click a button, make an API call, say, hey, I want to relaunch this guy. Your cluster becomes available almost immediately, probably within 10 minutes. And then your data streams directly from S3 into the query engine. So there's no need to wait for all that data to reach your cluster nodes. S3 is very, very reliable. It's probably the most reliable part of the AWS cloud. So it's a pretty good answer. Does that make sense? Yeah.
Yeah, question. So I was going to ask you this earlier in your earlier diagrams with the data sources. Is that why there was all S3 and DynamoDB listed there, or is there a larger universe?
No, that's it for now. So the data in S3 is stored in a couple of places. So there's data that's visible to you, so that's data you're going to load. So you kind of stage it in S3, and then you load it into the cluster. But then behind the scenes, Redshift itself keeps snapshot data in S3 in some sort of not obvious area. That's not, it's not obvious to you. It's not exposed to you, but it's there. So whenever you reboot a cluster or a node goes down, it streams it from S3. So did that answer your question?
Yes, I wasn't sort of asking about the internals of how it stores things, but the left side of your diagram.
Right, S3 and DynamoDB. Yeah, right now that's it for now. It also uses, I didn't mention this because I don't really know anything about it, but there's AWS Data Pipeline, which I'm not too familiar with, but you can use that to ingest data into your Redshift clusters as well. But again, it's all still through S3 and DynamoDB.
So without sort of paying costs for twice as much storage in the Amazon cloud, does one tend to sort of destroy instances if they are sort of not constantly, if your data isn't sort of constantly streaming in?
Does one tend to destroy instances if you're...
Your S3 instances on the left side.
Oh, okay, so S3, it's just a managed service. You don't actually have S3 instances that you, I guess it wasn't clear in there. You don't have S3 instances that you have to worry about. It's just, S3 is just there. It's a service provided by Amazon, right?
Right.
So you don't have to worry about your S3 buckets being available or anything. They just are, right? So Amazon, whatever it does behind the scenes to make sure that your S3 data is always available, they obviously replicate it. There's all sorts of things in place to make sure that your S3 data is always there. And I've actually never seen it not be available. So it seems to be pretty reliable.
It can be not available after you immediately write it.
Well, that's true. That's true.
It's a lazy read and replication scheme.
That's a good point. S3 is eventually consistent.
Second connection, or even seconds, to even see it appear.
That's a good point. You can put things into S3 and then immediately attempt to retrieve them, and they won't be there. So sometimes it takes a minute, sometimes it takes 2 seconds. It's usually immediate, but there's no guarantee. So that is true. Sure.
I'm not sure you said this before. You said there's a limit on 1,000 tables per...
Per cluster, yeah. And you can't even get around that with schemas, because in Postgres and Redshift you can create multiple schemas, and it doesn't get around that limit. So that's I don't know. I don't know why the 1,000 limit. It's pretty severe, I think, but there's some reason for it. I don't know if there are plans to address that or not. Cluster resize. This is also very, very cool. Again, given things like anticipated increased retail traffic, or maybe a heavy stock trading day, or for whatever reason, it's very easy to upsize or downsize a cluster. Now, the caveat being that the cluster does enter read-only mode for the duration of the resize operation, which, if it's a large enough cluster, could take some time. I mean, in the order of days. I've seen it take a couple of days. So if you can tolerate a read-only cluster for 2 days when you're resizing a warehouse that's, say, 30 terabytes, that's kind of the penalty that you pay. But it is easy. I mean, that's the thing about AWS. It's just an API call, right? These are all just API calls or clicks of a button on a console. And then the resize will redistribute the data. So if you're going down, obviously, it has to do some consolidation. If you're going up, it has to redistribute some data. But the cluster always remains available to query. That's the important part. There's the concept of workload management, and this is basically how it buffers concurrent access to the cluster. There are queues, so if you don't specify it, all queries go to a default queue. You can create up to 8 of your own queues, so if you wanted to slice work up into, say, 1 queue for reports and 1 queue for ad hoc and 1 queue for long-running processes, you can do that kind of thing. They have this concept of slots. Each slot is just a percentage of CPU and memory. So if you have 10 slots, then 1 slot is 10% of the processing power of the cluster. And then if your query doesn't have a free slot available, it just sits and waits. And it's all available via system table, so you can see what queries are waiting, how long they've waiting. You have an entire history of it. You can see how long queries have waited in the past and that sort of thing. So that's pretty cool. As far as performance goes, now again, there might be some eye rolling appropriately on these next few slides, but these are comparisons between Redshift for different types of queries against Hive, admittedly Hive 0.1, not 0.11, and a couple other solutions, Impala, Shark. But it's just it's relative, right? You see the far left is the tiny little Redshift bar, and the far right is the Here's the Hadoop bar, or the Hive Hadoop bar. So this is for a scan query. I don't know how many orders of magnitude that is, but for an aggregate query, it's still pretty impressive. And you can see the numbers there. And again, please feel free to check out the link. That would be a good idea. And then for a join query, and again, obviously it's all relative, right? This is a specific join. I don't know if this was handcrafted to prove how well Redshift performs, but and it doesn't that the benchmark hopefully gives information as to the exact configuration of Hadoop and Hive on their cluster. This one? I can't hear you.
For the unit, it is milliseconds.
Oh, I believe it is. Yeah, I think so. I think it's seconds, actually. Yeah. Good question. Yeah, I do believe it's seconds. Security, obviously, with your data warehouse in the cloud, security is pretty important. So it's typical with Amazon Web Services. You can have credentials that are associated with an IAM account, which can be associated with what they call policy actions. So if you don't want someone to be able to, you have to explicitly grant permissions for someone to create and modify a cluster and reboot a cluster and restore from snapshot and all the dangerous things you can do. And also, obviously, query as well. So you can prevent specific AWS users from doing whatever you want them to do or not do. You can create cluster security groups, and these are also familiar to you if you're using AWS, but you can create a security group and associate it to a cluster. You can do things like restrict inbound and outbound IP traffic. You could restrict things to a specific IP address, or supply a sitter for a range of IP addresses. You can add your cluster to a virtual private cloud if you're set up that way. You can use cluster encryption if you don't mind a 20% degradation in performance. So in that case, each 1 meg data block gets its own unique randomly generated key, and those keys are further encrypted by a randomly generated cluster-specific key. And that cluster-specific key is encrypted and stored off-cluster outside the AWS network. I can picture like a room with a little box and a key and a guy, I don't know. And that key is only kept in memory on the cluster itself. So that's pretty interesting. Obviously, you can have SSL client connections. You wouldn't expect anything less. You can encrypt your data in transit through SSL. So Amazon creates and installs an SSL certificate on each cluster, and they're signed by a public CA, certificate authority, and it's publicly available at some well-known address. You can also encrypt your data in S3 that you want to load. So if you remember the copy statement, there's a specific encryption attribute that you can supply with your encryption key to decrypt your data, so it will be loaded. So it doesn't have to sit on S3 in a decrypted state if you don't want it to. So I don't know. What do you think? Does this anybody see any game-changing aspects to Amazon Redshift? Certainly the price, I would think. No opinions? Not a game changer? No? Yes? What?
Besides Kubernetes, what is the key difference with some like database cluster?
Well, I guess the biggest thing is it's to the degree that it's managed by Amazon.
It's a managed database.
It's fully managed. So I didn't show any of the exposed APIs, but it's very, very rich. So you get the full infrastructure. So not only all of the management and operations type things you can do with a cluster, such as resizing, rebooting, and taking snapshots and all that sort of thing. But you also have there's like a rich incorporation with all the metrics you can capture. It's like the whole Amazon managed environment. So is it enough to get someone to buy into AWS just for Redshift? It might be, and especially if you consider the cost. $1,000 per terabyte per month, and declining, probably in the not near future, is pretty significant. Oh, sorry. Sorry.
So in a typical warehouse, we have some kind of pre-aggregation done and queues, so the data maybe is faster. So I never.
Yeah, this isn't it's not an OLAP type solution. It's
Everything is real time, query time, every aggregation is.
I mean, yeah, other than the fact that you can still do like any relational store, materialized views or whatever. But other than that, yeah, it is exactly. Yeah, it's not like a Cognos or anything like that. But like I said, all those I threw up the list of all the partners. So a lot of those BI solutions are exactly what you're describing, and they certainly plug into Redshift pretty easily.
Oh, so I have a question. I have more an opinion. Is it a game changer?
Yeah.
I love your talk. I'm a Hive committer.
Okay.
And I'm very interested in how they've chosen Hadoop and Hive to be the whipping boy of how great they're performing.
Well, to be honest with you, that's not Amazon, right? So those are third parties, right? So Amazon has not done that because they clearly have skin in the game. So Amazon has Elastic MapReduce, which is a perfectly good solution. I've used it quite a lot, so yeah, I don't know. Others have chosen Hadoop and Hive to be. I mean, I guess they have to do their comparison against something, right? And they.
It's like, like you brought out the benchmark. You said, oh, I dumped data in and I ran this query, but then you went on to show the slide about how the second day
Yeah.
you have to run this remerge command.
Right.
So like I feel that no one's going to take that into account. So you could always like insert data, wait an hour, and then run one query and be like, oh, this one query in my microcosm world is so great. But I mean, like our data warehouse may have 10,000 tables with 1,000 partitions each. And so you said, hey, there's only 1,000 table limit. So when you hit the 1,000 table limit in this game-changing warehouse, what do you do?
Right.
I don't,
That is an excellent point. No, it's a very, very good point. So, yeah, so there's overhead that's not accounted for in some of those slides, right? I really encourage you to click through some of those links, but I know it's not accounted for in some of those posts either. But yeah, like the vacuum overhead is not accounted for in any of those times, right? The degradation in cluster that you're going to experience while you're vacuuming is also not accounted for in any of those times. Now, if you happen to have a schema that, maybe, I don't know if it's most scenarios or some scenarios where vacuum times are low because you just happen to be always storing data in time series order, right? Then the overhead is minimal. But how common is that? Maybe more common than not? I don't know. It's a good question. Okay. Well, questions, I think we're already there. Any more questions? No? All right, sweet. Thanks. Thank you very much.